When we create a new file specification window appears. KYpipe loads an initial pipe schedule depending on the selections made here. For instance, the initial settings are for a system type of KYpipe. We're using English units, and the liquid type is water. If we create a new file using these settings, and we go to the Components menu and click on Pipe Type Management, the pipe type table appears along with a default pipe schedule. Each pipe type has preset data for the following characteristics: material, nominal diameter, reference roughness, estimated 10-year roughness, wall reaction rate, bulk reaction rate, and wave speed. Wave speed is used for surge applications, and the reaction rates are used for water quality simulations, so we won't discuss them further in this video. Because we chose English units, the nominal pipe diameter is in units of inches, and because we chose water as our liquid, our reference roughness values are Hazen-Williams C factors. If we load a new file but specify SI units instead of English units, we can navigate to the pipe type table, where we see the nominal diameter is now in units of millimeters. But since we didn't change the liquid type, we're still seeing the Hazen-Williams C factors. If we load a new file, but specify a liquid other than water, the Hazen-Williams friction equation no longer applies. So we can see in the System Data menu, KYpipe switches to the Darcy-Weisbach friction equation. As Hazen-Williams C factors no longer represent roughness, the Darcy-Weisbach roughness coefficients appear in the pipe type table. As a note, GoFlow loads a different pipe schedule than KYpipe does. Let's say we've built the system and we want to change the units and the friction equation. For instance, in this example, we've decided to change from metric units and the Darcy-Weisbach equation to English units and the Hazen-Williams equation. The pipe type table doesn't update automatically, but we can update it manually. If we click on the Load Original Default button, KYpipe detects the settings in the System Data menu and loads the correct pipe type table, which updates the nominal diameter and roughness columns. The default pipe schedule contains a fair cross-section of the type of pipes the user might want. It includes various diameters of ductile iron pipes, concrete pipes, and PVC. However, there are other schedules loaded into the software which can be accessed by clicking the New Pipe Schedule drop-down arrow. Most of these pipe types are used by the fire sprinkler industry and consist of smaller diameter pipes such as Allied 10. We can load the original pipe schedule by clicking this button. Also, this table can be customized. First, we can add a new pipe type by entering the information in a blank row. For instance, I'll create a steel pipe with a diameter of 6 inches and a roughness of 135, as well as an 8-inch steel pipe with the same roughness. Ideally, we would have a 10-year roughness value for this new pipe type. Of course, as time goes by, friction losses within the pipe increase, so the Hazen-Williams C factor decreases thus the estimated 10-year roughness value should be lower than the reference roughness value. Now if we go to the map view and add a pipe, and we click on it to select it, the pipe's information appears in the Pipe Info window. Pipes are created with a default type. To change that type, we click in the Pipe Type field, and a menu called Select Pipe Type appears. Here we see that all the pipes in the default pipe schedule are available, including the steel pipes that we added earlier. A second way to add a new pipe type is to click in the Pipe Type field, and within the Select Pipe Type menu, there is a Create New Type button. Clicking on this brings up the Add New Pipe Type menu. We can enter the information for a new pipe type here, which results in a new pipe being added to the pipe type table. We don't yet have a 10-inch steel pipe, so we can add that from this menu. We can verify that the new pipe type has been added, either by looking at the pipe type table or simply by bringing up the Select Pipe Type menu. Here we see our 10-inch steel pipe. A third way to add a new pipe type is to enter the data straight from the Pipe Info window. First, we'll uncheck the Display Pipe Type as One Item button. This button is normally active, and as a result, the pipe material, pressure rating, and diameter are all displayed in a single field. When we uncheck the button, these characteristics are disaggregated and can be edited individually. If we want to add a 12-inch steel pipe, we can click on the diameter field and enter the new value. Next, we select the pipe, which brings up the Add New Pipe Type menu. From here, we can change any of the other values as needed. After we click OK, we can see that the pipe type has been changed to 12-inch steel. Here we see our 12-inch steel pipe. Now that we've altered the pipe type table, we may wish to save this new pipe schedule for use in other projects. Click on the Save button and give the project a file name. We'll call this Lexington Pipes. By default, the pipe schedule file is stored in the Schedule folder. Once a pipe schedule is stored in this folder, it's available for any project, not just the one it was created in. We can click the New Pipe Schedule drop-down arrow to see and load the schedule we just created. If you want to share a custom pipe schedule with other users, the pipe schedule file will have a .mat extension. When you transfer the file to another computer, copy it to the same location, which will make your custom pipe type file available in the drop-down list in the Pipe Type Management menu. In the pipe type table, we have a column for actual diameter and for nominal diameter. If you know the actual diameter of a pipe, you can enter it here. By default, the program uses the actual diameter for calculations, as we can see by looking at the Diameter for Analysis menu. We could change this by clicking the radio button for nominal diameter, which causes KYpipe to run an analysis using that instead of the actual diameter. But again, the default setting is for the actual diameter to be used for the analysis. Normally, the nominal diameter is only used for display purposes. However, under the default setting, if there is no actual diameter entered, then the nominal diameter will be used instead. Also, if the actual diameter has a 0 value, then the program uses the nominal diameter. For instance, there is one 8-inch PVC pipe in this model. if we enter an actual diameter and run the analysis, we can click on the Report button and see that KYpipe used the actual diameter for this pipe, but it used the nominal diameter for all the other 4-inch pipes, since we didn't enter an actual diameter for them. However, back in the map view, we can see that the nominal diameter is used to describe the pipe instead of the actual diameter. The actual diameter column is a good place to look if you are seeing unexpectedly low pressures and flows in a part of your system, since any errors here aren't normally shown in the pipe info window within the map area. If we wish to see the actual diameter within the map area, we can click on the Display Actual Diameter button, which adds that field to the pipe info window. In addition, if we mouse over the pipe, the cursor notation shows the actual diameter in addition to the nominal diameter. Cursor notations are controlled from this menu. KYpipe's default setting allows the simulation of pipe aging using the 10-year estimated roughness values in the pipe type table. Within the pipe type table, we see there are 3 options. As stated, the radio button for the default option is currently checked. Another option is to use the reference roughness only, which will turn off pipe aging. The third option allows you to determine the roughness values for the pipes in your system using KYpipe's calibration module. This relies on field data, which is usually in the form of fire hydrant flow tests. Running the calibration module will generate new values to match the field test data as closely as possible. These new values are entered in the Calibrated Multipliers column and Calibrated 10-Year Roughness column for each pipe. Then, if you run an analysis, the program will use these values for pipe aging as long as this radio button is checked. For now, let's go back to the default option, which allows pipe aging and uses the 10-year estimated roughness. There are a few different ways we could utilize pipe aging. First, we can see what effects older pipes have on an analysis run in the present. This project was created in 2017. When I click on a pipe to highlight it, we see that the install year is the current year. Let's change the install year, say to 1980. This causes KYpipe to recalculate the current year pipe roughness, although first we need to click on the pipe to see the change. We could now run an analysis with the new roughness. So that's the first way we can use pipe aging. The second way we can see the effects of aging is to run a future analysis on a pipe that is currently being installed. However, not only does the install year default to the current year, but the analysis year does as well. Therefore, without further input, the system will model pipes installed in 2017 in the year 2017. Thus, pipe aging is not initially a factor, unless we either change a setting or open this file in subsequent calendar years and run it again. For instance, if we ran this file again in 2018, KYpipe would apply 1 year of aging automatically. But we probably don't want to wait that long, so let's change the setting for the year the analysis is carried out. First, we'll click the Quick Analysis button so we have some baseline values for pressure and flow. Now, to assign a different simulation year, we click on the Analysis menu, then click on Analyze. Here we see the Use Current Analysis Year box is checked. If we uncheck it, we can enter a different year. Let's say 2025. Now we can click Analyze and see the results. In case we didn't remember the baseline conditions, KYpipe stores the results of the prior analysis, and these can be seen by clicking in the Node Info window or the Pipe Info window. Click the Show Graph in Table button or the Table button, then click the Display Previous Results button. Here we see the difference between the two analyses. As we would predict, the flow is lower in the current analysis, which is for the year 2025, than the prior analysis, which was for 2017. Third, we could do some combination of the above two scenarios. That is, we could run a future analysis of pipes installed in the past. In the simulation, if we click on the Install Year row header to enter Group Edit mode, we can create a new value for the install year, say 1980, and apply it to all the pipes in the model. Then, if we run an analysis, we will be modeling the effects of pipes installed in 1980 in the year 2025. If we want to know the roughness value used for the analysis, we can click on the Report button and see the roughness coefficient in the data summary for each pipe. This is the projected roughness after the 45 years between 1980 and 2025 have elapsed. Note that pipe aging calculations depend on the 10-year roughness values entered in the pipe type table. If the estimated roughness values are missing, the program defaults to the reference roughness, whether or not we told it to use pipe aging. For instance, in the scenario we just ran, we were using estimated values. If I go to the pipe type table and delete the 10-year roughness value for a given pipe, then the pipe aging calculation is not applied to that pipe. Another thing to consider is that the roughness field must be unfixed in order for KYpipe to calculate an age-related roughness for a given pipe. In the file we ran earlier, we saw that changing the install year to a point in the past causes KYpipe to recalculate the roughness for that pipe. However, this works only if the roughness field is unfixed. Currently, we see the field is shaded a lighter color than the rest of the fields in the Pipe Info window, indicating that its status is unfixed. However, if I enter a value manually, the field becomes fixed, and the color of the field is now the same shade of blue as the rest of the fields in the Pipe Info window, indicating its fixed status. Now, changing the install year does not alter the roughness. Therefore, it's important to check the status of the roughness field for your pipes when doing an age progression. If any of the fields are fixed, you can unfix them by clicking on the row header, then edit type of unfix, calculate, apply the edit, and press OK. If you have a very large project and are not sure which pipes have unfixed roughness fields, you can select all the pipes in the Edit menu, then group edit the pipes, and apply Unfix Calculate. We now see that the roughness field is colored a lighter shade of blue than the rest of the fields in the pipe info window, which confirms that the field is again unfixed. If you have field data, specifically measurements of pipe roughness, you can use those data to generate estimated 10-year roughness values. To do so, we go to the Tools menu and launch the 10-year roughness estimating tool, or the Hazen-Williams coefficient tool. To use this tool, we'll need to know three things. The first is the age of the pipe, which in this example will be 45 years. Next will be the roughness as determined by the field test, which will be 105. Third, we'll need to know the roughness when the pipe was installed. Let's say it was 130. Once we enter these figures, the tool calculates the 10-year estimated roughness, which for this pipe is 121.85. There are some other methods that can be used, but using pipe roughness data is the most common. We then enter this value into the pipe type table. If desired, we can save this change to our Lexington Pipes file in the Schedule folder for use in another project.